Swayam Prabha. Digital India. Educated India.
In today's lecture, we are going to do the stability analysis, and today's lecture will be in the form of a tutorial. We take a specific problem and then try to do it on the board so that you can follow closely what I am doing, and then you can replicate it for other problems of your interest. Today's problem is to do a stability analysis for the same one-dimensional wave equation which we have been considering earlier, but with an implicit scheme. So, we are going to do FTCS scheme for the one-dimensional linear wave equation. And what we mean by FTCS scheme is forward in time, central in space, but an implicit scheme. And we will try to do the von Neumann stability analysis for this and investigate the stability conditions for this particular case. So, it is a tutorial on von Neumann stability analysis. The equation that we take is dou u by dou t plus a dou u by dou x equal to 0. This is on a domain 0 less than x less than capital L, and with uniform grid spacing of delta x with periodic boundary conditions, so that and A is constant. Therefore, we have a linear equation with periodic boundary conditions, uniform grid spacing, and a one-dimensional form. We can apply the von Neumann stability analysis for this, and we are going to consider the forward in time, central in space, implicit scheme. Discretization, so that we can write this as ui n plus 1 minus ui n by delta t is the forward discretization, forward differencing for the time derivative, plus a time central in space. So, this will be u I plus 1 minus u I minus 1 by 2 delta x. Since it is implicit, the space derivative is evaluated at n plus 1, and this is equal to 0. So, this is our discretization scheme, and we can also write this as, we can take this delta t this side and get an explicit formula for this. So, when we have a scheme like this and we want to investigate the stability using the von Neumann stability analysis, we consider D to be the exact solution and N to be the numerically computed solution, and epsilon to be the error. Okay, and each of these is a function of both x and t, because we have this u here is a function of x and t. Therefore, we denote the space x by the space index I and the time by the time index superscript n here, and this will be the exact solution at time of xt, and this is also at time of x and t, and this is at time of x and t. And as the solution progresses, d also changes, din is changing and nin is changing and epsilon in is changing, and we say that the numerical solution is the exact solution plus an error, and therefore we can say that n is din like this. And what this means is that we have an exact solution plus an error which is changing at a particular location with time, because as n changes, it changes. And if the scheme is such that this error can accumulate, then if we run enough number of these time steps, the accumulated error may become much bigger than this, so as to give us an computed solution n which does not look like d. As long as epsilon is very small, n will be almost equal to d. Okay. If epsilon is growing, then after certain number of time steps, epsilon will become large. It will become so large that n will be more like error than like d, and that is what we would like to avoid. So we would like to see under what conditions the error will grow and eventually take us to a situation where this error dominates the exact solution, and therefore the computed solution is no longer like the exact solution. So this is the stability idea, and we are going to define an amplification factor which is error at a particular spatial location at n plus 1 time divided by error at the same spatial location at n. And if the amplitude of this, if mod g is less than 1, then we can say that error will not grow. Okay. If it is greater than 1, we have possibility of the error increasing with time in magnitude, and therefore overwhelming the exact solution to give rise to a computed solution which is no longer like the exact solution. So for g, mod of g less than 1, we have stability, and mod of g is greater than 1, we have instability, and that is what we should be avoiding. So under what conditions is this particular scheme stable is the situation that we would like to evaluate. And for that, for a linear initial value problem with periodic boundary conditions, we can make use of the Neumann bound analysis, wherein we decompose the error at x of t into a sum of Fourier components, and m varies from 0 to capital M, and m is given by km is given by m pi by L, and m is 0, 1, 2 up to capital M, where capital M is L by delta x. Okay. So these are the Fourier components, these are the m capital M plus 1 number of Fourier components which are present in this series, and each of this is a sinusoidal component with an amplitude and with a sinusoidal variation given by this exponential this function with j equal to square root of minus 1. And because we are looking at a linear equation, the contribution of each of these Fourier components can be added at any time to give rise to the total error at a particular spatial location at that particular temporal location. And because this superposition principle is possible to look at the evolution of the error, we can take any particular wave component and we try to investigate the stability condition. So we look at the specific component mth wave component at location I and time step location n, and we write this as Bm minus j km delta x, where km is the corresponding wave number for this. And because we are going to look at whether it is going to increase with time, and we are going to take the ratio here, we can also write this as exponential of a n delta t exponential of j km delta x here. Okay, so that this is at time t, and the error of the same component, mth wave component, at the same location at the next time step n plus 1 is therefore given by exponential of a times, no, we have already used a here. Let's change this, it's easier, as u naught. In a way, it's a linearized convection term. So we can retain this n plus 1 times delta t j km delta x here. And the ratio between the two is essentially for the mth wave component n plus 1 divided by the same component at the same location but at nth time is now given by exponential of a delta t. And therefore, if a is positive, then this is going to be a positive quantity, and if it is greater than 1 in magnitude, then it is going to give rise to instability. So we take this particular wave component and then we substitute that in our formula here, starting with this, and we can call this as equation 1, and the numerical value that we get here is obtained from this. So we can say that equation 1 is satisfied so as to give rise to Ni n plus 1 minus Nin divided by delta t plus u naught times Ni plus 1 n plus 1 minus Ni minus 1 n plus 1 divided by 2 delta x equal to 0. So this is our second equation, and we also know that din is an exact solution, and we can also say that din plus 1 minus din divided by delta t plus u naught times di plus 1 n plus 1 minus di minus 1 n plus 1 by 2 delta x equal to 0, and that is equation number 3 here. And we also have this expression, and we can substitute this here, and then we can get a fourth expression, which is din plus 1 plus epsilon in plus 1 is this quantity minus din plus din minus plus epsilon in, this whole thing divided by delta t plus u naught times this here, which is di plus 1 n plus 1 plus epsilon I plus 1 n plus 1 minus di minus 1 n plus 1 plus epsilon I minus 1 n plus 1, this whole thing. Okay, so this minus this whole thing divided by 2 delta x equal to 0. Now we can club all these d's together and we will be getting this, and this whole thing is equal to 0. And once we take out the d components, we will have an error evaluation equation as epsilon I n plus 1 epsilon I n plus 1 minus epsilon I n divided by delta t plus u naught by 2 delta x times epsilon I plus 1 n plus 1 minus epsilon I minus 1 n plus 1 equal to 0. Okay. So, we can now take this delta t here, so that we have times delta t, which is still equal to 0, and this can be written u naught delta t by delta x is a courant number sigma. So, we can write this as epsilon I at n plus 1 minus epsilon I n plus sigma by 2 times epsilon I plus 1 n plus 1 minus epsilon I minus 1 n plus 1 equal to 0. So, this is the error equation here, and then this error equation is decomposed into so many Fourier components, and we look at the nth component of this here, and therefore, we substitute this form into here, and we can write this as the mth component will be exponential of a n plus 1 delta t exponential of j km I delta x. I think here I forgot to put I throughout because this is at x. So, this should be I times delta x. Okay, so, this is this term minus exponential of a n delta t exponential of j km I delta x plus sigma by 2 times exponential of a n plus 1 times delta t exponential of j km times I plus 1 delta x minus exponential of a n plus 1 delta t exponential of j km I minus 1 delta x. So, this whole thing is equal to 0. So, this each of this term, this whole equation is now divided by this term. Okay, so that we have, if we divide by this, we get a delta t, because this and this will cancel out, and the n part will cancel out with this, and we get exponential of a delta t minus 1 plus sigma by 2 here, and here a n delta t again will cancel out here, leaving this exponential of a delta t, and similarly here exponential of a delta t will be there. So, we can write this as exponential of a delta t times, here in this km I delta x cancel out, we will have e j km delta x minus, here again this is already considered, and I delta x will cancel out, and we will have minus j km delta x with the minus sign, and this whole thing is equal to 0. Okay, so, we have now this equation is just a simplification of this, in which we have substituted the mth wave component in the error propagation equation here, and divided by this quantity in order to get G, because this is precisely what our amplification factor is, because this is epsilon I n plus 1 by epsilon I n, and that gives us this. So this is our G here. Okay, so we can write this as G minus 1 plus sigma by 2, this is again G, times E j phi minus E minus j phi equal to 0, where phi is equal to km delta x. And as we have mentioned earlier, as km changes, as the wave number changes, this phi will take values from 0 to pi. Okay. So in that sense, we can virtually take this phi to be a continuous function from 0 to pi, even though it has a discrete values. So as delta x tends to smaller and smaller values, capital M becomes larger and larger. So that means that the number of steps taken to go from 0 to pi will increase, and it becomes, in the limiting case of delta x tending to 0, it becomes almost a continuous function of phi all the way from 0 to pi. And we also have the relation that E j phi is cosine phi plus j sin phi, and E minus j phi is cosine phi minus j sin phi here. And so if you take this to this minus this, you will be getting minus 2j sin phi, G minus 1 plus sigma by 2 times G times 2j sin phi equal to 0, or G equal to 1 by, so this 2 and this 2 will cancel out, and so we get G times 1 plus sigma j sin phi minus 1 equal to 0, or G equal to 1 by 1 plus j sigma sin phi. This is our amplification factor. Okay. So now we have to investigate the conditions of under which G is going to be greater than 1. So we have G equal to 1 by 1 plus j sigma sin phi, and we can multiply and divide by 1 minus j sigma sin phi, so as to get 1 minus sigma j sin phi, and we get 1 minus sigma square j square sin phi, and j square is minus 1. So we get 1 plus sigma square sin phi, sin square phi. This is a real quantity, and therefore this is our G here. So therefore we can write this G as 1 minus j sigma sin phi by 1 plus sigma square sin square phi, and the complex conjugate G star will be just 1 plus j sigma sin phi divided by 1 plus sigma square sin square phi, and we can write the square of the modulus of G as G times G star, and this is equal to 1 minus j sigma sin phi times 1 plus j sigma sin phi divided by 1 plus sigma square sin square phi whole square, because it's the same thing which is common, and this again gives us 1 plus sigma square sin square phi So, therefore, it is 1 plus sigma square sine square phi. Okay. So, this is square of the magnitude. The numerator gives us 1 plus sigma square sine square phi. So, we cancel with one of these and then we have this. And what we see is that this is always less than 1. In the special case where phi is equal to 0 or 180, then this is equal to 1. Okay. Because sigma is u naught delta by delta t by delta x and we have sigma square here, then this is always less than or equal to 1 and therefore, it is always stable. This is in contrast to the FTCS in the case of FTCS explicit, where we put this as uin plus 1 n and ui minus 1 n here, then we have seen that G in this case is equal to 1 minus j sigma sine phi, and therefore, G star is 1 plus sigma j sine phi, and therefore, the square of the modulus is G times G star, and that is equal to 1 plus sigma square sine square phi, and this is always greater than or equal to 1, okay, except for the special case of phi equal to 0 or 180, this is greater than 1. So, that means that this is always unstable. So, the same FTCS explicit version is always unstable, but the implicit version is always stable, and this is something that we get usually when we go from stability from a stability point of view from explicit method to implicit method. There are explicit methods which are unconditionally stable, just like this FTCS implicit, and there are explicit methods which are unconditionally unstable, like this one here. But usually when an explicit method is conditionally stable or unstable, the corresponding implicit method is very likely to be to prove unconditionally stable, and therefore, when we go for an implicit method, then we gain in terms of stability, okay, and that is something that we would like to demonstrate, and I hope from this tutorial we have learnt the mechanics of how to do the von Neumann stability analysis for a given discretization scheme. So, we start with finding the error evaluation equation, either this or this, from the discretization, and then we investigate the stability of the mth wave component by substituting the corresponding expression for epsilon in as epsilon a n delta t times epsilon j km I delta x here, and then we find the amplification factor, and from the amplification factor we find the magnitude, and we see under what conditions the magnitude is greater than 1, and if the magnitude is greater than 1 for certain conditions, then it is conditionally stable or conditionally unstable. If for all conditions, if the magnitude is greater than 1, then it is always unstable, and if for all conditions of sigma and phi and all that, if it is stable, if it is less than 1, it is always stable. In the next class, we are going to look at some more schemes, and then we are going to look at the stability analysis, and we will move on to the one dimensional scalar transport equation and look at the stability.